Here we discuss the waveguides. In the previous session, we have studied the properties of the transmission lines, and we have also seen the characteristic properties of the transverse electromagnetic waves, which are guided by the transmission lines. So in transverse electromagnetic waves, both electric and magnetic fields are transversed to the direction of propagation of the wave. The electric and magnetic fields are perpendicular to each other, and both are perpendicular or transverse to the direction of propagation along the guiding line. So in the case of transmission line, suppose the guiding direction is along Z direction, then electric and magnetic fields are perpendicular to the Z direction. That means the electric and magnetic fields do not have the longitudinal component or Z component. And one important property of the transverse electromagnetic waves guided by the transmission lines having negligible resistance is that the velocity of propagation of the wave having any frequency is same as that of the velocity of propagation of the transverse electromagnetic wave in the unbounded dielectric medium. So we know that in an unbounded dielectric medium, the velocity of propagation of a transverse electromagnetic wave is equal to c divided by the refractive index of that medium. So similarly, in the case of the transmission line also, the velocity of propagation of the wave, transverse electromagnetic wave, is equal to this c divided by n, or c divided by root mu r epsilon r. C is 1 over root mu 0 epsilon 0, or this can be also written as 1 divided by root mu epsilon. So this velocity is same for a TEM wave in a lossless or a low loss transmission line, as well as the unguided transverse electromagnetic wave propagating through an unbounded dielectric medium. Unbounded means a medium without any boundaries. Okay. And in the previous session, we have studied the three types of transmission lines: the parallel plate transmission line, two-wire transmission line, and coaxial transmission line. And we have seen that they are the special type of waveguiding structures. So these are not the only waveguiding structures. There are other types of waveguiding structures as well. And in this session, we are going to learn about the other waveguiding structures. And we have already seen that in a lossless transmission line, the TEM wave can propagate without any longitudinal components. So if the transmission line is lossy, it has got a longitudinal EZ component which is very small, and we found that this EZ is proportional to frequency. So as frequency increases, this longitudinal component also increases in magnitude, and the transverse electromagnetic nature is being lost at high frequencies. So, the transverse electromagnetic waves are not the only mode of guided waves that can propagate through the transmission lines. So, through the transmission lines, the TEM as well as TM and TE modes can propagate. So, TM mode is transverse magnetic mode. That means the magnetic field is only transverse or perpendicular to the direction of propagation, and therefore it has got a longitudinal electric field component. An electric field component along the direction of propagation. And the other mode is TE mode. So, which is transverse electric mode. That means the electric field is perpendicular to the direction of propagation. So, but magnetic field is not perpendicular, and therefore it has got a longitudinal magnetic field component. So, these are the other two modes. So, all these three modes can pass through a transmission line. And the transmission lines are not the only waveguiding structures. There are other waveguiding structures as well. So, the waveguiding structures are generally called waveguides. And the transmission lines are a special type of waveguides and which pass TEM through it. The other waveguides will not pass transverse electromagnetic waves through them. So they can only pass TM and TE mode. And the characteristic properties of this mode is that they have a cutoff frequency. That means the waves of frequencies below the cutoff frequency cannot propagate. So, only those waves having frequencies greater than or equal to the cutoff frequency can pass through the waveguides in the case of TE and TM mode. So, they act as high-pass filters. They pass the waves when frequency is greater than the given cutoff frequency of that mode. Therefore, they act as high-pass filters. So, that means only those waves having frequency greater than the cutoff frequency is allowed to pass through this waveguides. And those waves having frequency less than the cutoff frequency are not allowed to pass through. So now in this part we study a general analysis of the characteristics of the waves propagating along uniform guiding structures. So here we study waveguides or guiding structures having uniform cross section. So that means the waveguides having only one conductor in it. So here we are studying the properties of single conductor waveguides, and we will see that the single conductor waveguides cannot pass TEM waves through it. And we have seen that the transmission lines are double conductor waveguides like a parallel plate, a two wire and coaxial, and they can pass transverse electromagnetic waves through them. But the single conductor waveguides cannot pass the transverse electromagnetic waves through them. So the transmission lines are the only waveguiding structures that can pass transverse electromagnetic waves through them. So the three types of waveguides that pass transverse electromagnetic waves are parallel plate transmission line, coaxial transmission line, and two-wire transmission line. But single conductor waveguides cannot pass transverse electromagnetic waves through them. So they can only propagate TM mode or TE mode through them. Okay.